Chapter 7, Techniques of Integration, Section 7.1, Integration by Parts. So we now have a formula for integration by parts where if f and g are differentiable functions, then the integral of f times the derivative of g is equal to f times g minus the integral of g times the derivative of f. What we usually do is we write it in this shorthand notation where the integral of u dv is equal to uv minus integral of v du. So what this basically is the product rule in reverse. What we do is we look at an integral that has a product in it, so it might be tricky to evaluate. However, we break it down into a product without an integral and a product within an integral. You might be saying, well, this is even worse than what you started with because now you've got an integral and you've got something else. But usually what we do is we choose f and g or u and dv such that this integral that I circled will be simpler than the original integral. So proving this is really quick, we just use the product rule. Remember that the derivative of product is the first function times derivative of second plus the second function times derivative of first. So if we integrate both sides, remember that integrals, indefinite integrals are antiderivatives by definition. So that gets rid of my d dx, and I just have f times g is equal to the integral of the product rule. But remember that the integral of a sum is the sum of the integrals, so I can split it into two integrals. And then I can just subtract an integral from both sides. So I subtract, I subtract this integral from both sides, and I get that this thing minus this thing is equal to this thing, which is the exact integration by parts formula that I wanted to prove. So how about we find the integral of x sine x dx? Notice that there's a product inside, so we need our integration by parts or reverse product rule. So we need to let u equal something, and we need to let dv equal something. So remember that u is going to end up becoming du when we differentiate, whereas dv will end up becoming v because we'll have to integrate. So when we choose what we want u to equal, we should probably try to choose something that becomes simpler when you take the derivative. So how about we choose x, because that's a polynomial. When we differentiate any polynomial, the power always goes down by 1, so it usually becomes simpler. So how about we let u equal x, then we let dv equal sine x dx, so that du is the derivative, which is dx, or 1 dx, and we integrate to find v, so when we integrate, we get that the antiderivative of sine is minus cosine, and that's v. So we've substituted everything we need to substitute. We can now actually plug it into our integrals, so x sine x dx is equal to u times v, so that's x times minus cosine x minus the integral of v du, so that's minus cosine x, and du is just dx. So when we actually simplify this a little bit, we get minus x cosine x plus the integral of cosine x dx. And like I said, you might be tempted to say, hey, this is not simpler, just still an integral. But this integral of just cosine is just the antiderivative of cosine. Way easier than this integral because that original integral had a product in it, and our end integral has no product. So this ends up becoming minus x cosine x plus sine x plus an arbitrary constant c. If we had chosen to make u equal sine x and dv equal to x dx, then we would take the derivative for u, so we'd get cosine x, but then we'd have to integrate dv to find v, so x dx would become x squared. So instead of getting to cosine over here, we would get x squared cosine, so our integral would become even worse. So you have to be a little bit careful with your choice of u and v. Kind of like when you're doing u substitution, you have to be a little bit careful of your choice of u. But it gets easier with practice. Let's integrate ln x dx. Notice that at first glance, it doesn't look like there's any product here. But if we're a little bit clever, we can let u equal ln x, and we can let dv equal just the dx. Because in this case, differentiating ln x is definitely simpler. You just get 1 over x dx. And integrating dx just gives you x. So we have v equals x, and we have u equals ln x. So we end up with our integral ln x dx equals u times v. So that's x ln x minus integral of v du. So that's just x times du is 1 over x dx. So I could write that as dx over x. And this becomes x ln x minus, the x's cancel, so it's just integral of dx. So that's x ln x minus x, because the integral of 1 is x, plus an arbitrary constant c. So now we have a formula for the integral of the natural log. Let's try finding the integral of t squared e to the t dt. So again, it's easiest to let u equal the polynomial, because that way when you differentiate it, it becomes simpler. So let's let u equal t squared, and then dv equals e to the t dt. Seems like that's a good choice for dv, because we can definitely integrate e to the t pretty easily. So we get du is equal to 2t dt, and we get that v is equal to e to the t. So then our integral is now the integral t squared e to the t dt equal to t squared e to the t, because that's u times v, and then minus the integral of v du, so that's minus the integral of e to the t 2t dt, so I could pull out the 2 and get t e to the t dt. So again, you know, very often with these problems, it looks like you haven't made any progress, but we actually have made extreme progress. We've gone from t squared to t. So we've gone down an entire exponent. So if it stands to reason, if we do this again, we should be able to get rid of t entirely, which would be great. So let's try that. Let u equal t this time. Let dv equal e to the t dt. We'll try integration by parts by taking du equal dt and taking v equal to e to the t. And then hopefully, like we thought would happen, the t will just disappear. So if we integrate t e to the t dt, now I'm just integrating this thing by itself. I use integration by parts a second time. I get t e to the t, that's u times v, minus the integral of v du, so that's minus the integral of e to the t dt. And I end up with t e to the t minus the antiderivative of this, which is just e to the t, and plus c. Okay, that's pretty wonderful now, because that means that this entire integral can be replaced with this, so we're out of integrals. Looks like we managed to figure it out. So t squared e to the t dt will equal t squared e to the t minus 2 times this integral that we just calculated. So we can now replace it. We get t squared e to the t minus 2 times t e to the t minus e to the t plus c. So we can simplify and distribute the 2. We get t squared e to the t minus 2t e to the t plus 2 e to the t minus 2c. So we have minus 2 times a constant, but the constant could have been anything. So 2 times the constant is just as arbitrary as any other constant, or minus 2 times the constant is just as arbitrary as any other constant. So how about we write that as just its own constant? We could write t squared e to the t minus 2t e to the t plus 2 e to the t plus c1, where we just replaced c, or minus 2 times c with c1. In general, we'll probably be even lazier, and in the end we might just write c over here, even though we already used it, because it really doesn't make any difference between writing c1 and writing c or d or any other letter. You know, 2 times the constant is still just as arbitrary as any other constant. Let's evaluate e to the x sine x dx. So there's nothing that really becomes that simpler when we differentiate. So we kind of have to just, you know, guess and wing it. So let's just let u equal e to the x and dv equal sine x dx, and let's just see what happens. We'll take du, it's, you know, just e to the x dx, so nothing much happened there. We'll take v, the antiderivative, and we get minus cosine x. So we try our substitution. We get e to the x sine x dx is equal to minus e to the x cosine x, because that's u times v, minus the integral of v du. So we have minus cosine, so this becomes plus when we do minus, minus. So we get e to the x cosine x dx. And it looks like we have not made any progress. However, doing integration by parts twice helped last time, so let's just persevere and just see if that manages to work itself out. So this time, let's let u equal e to the x and dv equal cosine x dx. And let's see if we can evaluate this integral over here. So du equals e to the x dx, and that means that v equals sine x when we take that antiderivative. So we write out our integral. We get e to the x cosine x dx is equal to u times v, so e to the x sine x minus the integral of v du, e to the x sine x dx. Okay, so now it looks like we're going in circles. We went from e to the x sine x to e to the x cosine x back to e to the x sine x. However, if we're really careful here, we might be able to notice that this entire thing can be plugged into that, and then we'll have a minus e to the sine x on one side and an e to the x sine x on the other. That's kind of like if I had an equation with x equal to, let's say, 1 minus x, then you'd be like, oh, that's awesome, just add x to both sides and you'll get 2x equals 1 and you'll be done. Well, that's exactly what we can do now. We've got an integral on both sides that's identical. So what we could do is we can write e to the x sine x dx, which is this, is equal to minus e to the x cosine x, which is this, plus this integral, which is this. So it's plus e to the x sine x minus the integral of e to the x sine x. So now we just add that integral to both sides. We end up with 2 times the integral e to the x sine x dx, just treat it like a variable, is equal to minus e to the x cosine x plus e to the x sine x. Okay, we could just divide by 2. We get e to the x sine x all by itself equal to half e to the x times sine x minus cosine x. I'm dividing by 2 and I'm factoring out e to the x at the same time. Because sine is positive, I'll write it first. Can't forget my arbitrary constant though. Okay, well, there's no reason why this shouldn't work with definite integrals, because you could just apply the fundamental theorem of calculus to part 2. So let's do an example where we have a definite integral and we want to do integration by parts. This is kind of similar to when we were doing the integral of the natural log. It's not immediately obvious that we have a product here, so let's just try letting u equal what we've got, that tan inverse, and we'll see what happens. Let dv equal dx. So then, remember, the derivative of tangent inverse is 1 over 1 plus x squared, so we get dx over 1 plus x squared for du, and for dv, when we integrate, we just get v equal to x. So our integral becomes the integral from 0 to 1 tan inverse x dx, the x times tan inverse x is our u times v, and we have to evaluate that from 0 to 1 because this is a definite integral. Then we subtract off the definite integral of v du, which in this case is x times 1 over x times 1 over 1 plus x squared dx. Tongue twister. So let's actually do this evaluations. We plug in 1, we get 1 times tan inverse of 1 minus 0 times tan inverse of 0. So that's nice, that'll be gone. And then we subtract off the integral from 0 to 1 of x over 1 plus x squared dx. So this ends up becoming pi over 4 minus the integral from 0 to 1 of x over 1 plus x squared dx. And unfortunately, that's not the easiest integral in the entire world, but it's also not the hardest. Remember that we still have our old tricks in our toolbox, especially when u substitution. So we've been doing uv substitution or udv substitution, but that doesn't preclude us from using u substitution. Notice that in the bottom we have a 1 plus x squared. If we were to let u equal that, then the derivative would be 2x dx. So we'd be able to eliminate the top piece. We already used u though at the top over here, so we probably need another variable so we don't get confused. So instead of u substitution, how about we make this t substitution? So we have a new variable. So let t equal 1 plus x squared. So that means that dt is 2x dx. So solving for x dx, we get that x dx is equal to half dt. So that's all we have to plug in. We have to be a little bit careful though. Remember, this is a definite integral, so we need to change our limits also. We've got x equals 0. If I plug in 0 for x, I get that t is 1 plus 0. So that means that t is 1 when x is 0. And if I look at x equals 1, then 1 squared plus 1 is 2, so t is equal to 2 over there. So I think now I have enough I can actually evaluate this integral. I'll say that the integral from 0 to 1 of x over 1 plus x squared dx is equal to half times the integral from 1 to 2 of dt over t. Because I can pull out the half because it's a constant, and I end up with u on the bottom, or t on the bottom. So this is just half times the natural log of the absolute value of t when you take the antiderivative, and we evaluate that from 1 to 2. So that's half of ln 2 minus ln 1, but ln 1 is 0, so that's just half ln 2. Alright, pretty nice. So our integral from 0 to 1 of tan inverse of x dx was equal to pi over 4 minus the integral from 0 to 1 of x over 1 plus x squared dx. That's what we calculated over here. But we now know that that's pi over 4 minus ln 2 over 2. let's prove the reduction formula, sine to the n x dx. Notice that we call this a reduction formula because the integrand sine to the n becomes, gets a smaller exponent and becomes sine to the n minus 2. So you can see how this could be useful, because if we can prove this formula, which of course we will, then we'll be able to take any power of the sine function, and because we can always translate, we could take any power of the cosine function, or we could just prove another formula for cosine, and we'd be able to integrate it by just doing this formula enough times so that it keeps reducing by 2 and reducing by 2. If it's an odd exponent, eventually we'll just get down to sine to the 1, which is sine. And if it's an even exponent, eventually we'll just get the integral of of sine to the 0 power, which is 1. So in any case, this could come in handy. Let's let u equal sine to the n minus 1. So what I'm doing is I'm rewriting the integral of sine to the n as sine to the n minus 1 times sine. So that means that dv will be equal to the rest of inside of our integral, which is sine. So when we take du, we get the chain rule going on over here. So this hops out in front. So we have n minus 1 times sine to the n minus 2. And we can't forget to multiply by the derivative of sine. So we have to multiply by cosine. And let's see if I can just move this over real quick. And we can get that v is equal to minus cosine when we take the antiderivative. So that means that the integral of sine to the n x dx is equal to minus cosine x times sine to the n minus 1x, that's what u times v is equal to, plus the integral of v du. So we'll have minus cosine x inside, and we'll have this entire mess. Notice that we subtract, so actually this should be minus over here, but I'm about to change that back to a plus, because when we subtract the integral of v du, in this case we're subtracting a negative because of that cosine, so we'll be able to add, and this n minus 1 has nothing to do with x. It's a constant in terms of x, so I can pull that outside of the integral. So I end up with sine to the n minus 2 times cosine, so that's times cosine squared. Okay, I have to be pretty careful not to forget any of these x's. I keep forgetting them. So we end up with minus cosine sine to the n minus 1 plus n minus 1 times the integral of sine to the n minus 2 times 1 minus sine squared. Because remember, cosine squared plus sine squared is equal to 1. So I can replace cosine entirely and just have an integral with sines in it. Also notice that we wanted to end up with sine to the n minus 2, and we have a sine to the n minus 2. So we're definitely making some sort of progress, it seems. So this becomes minus cosine x sine to the n minus 1 plus n minus 1 times the integral of sine to the n minus 2 minus n minus 1 times the integral of sine to the n. But we just distribute this. When we distribute, this one becomes this one. This one, when you multiply by 1, becomes my first integral. And then the second arrow, sine to the n minus 2 times sine squared, the 2's cancel and just leave you with sine to the n. And then you can't forget that this thing gets distributed also to each of the integrals. Okay, So as before, it seems like we have not made much progress because we have sine to the n still, and we only wanted to have sine to the n minus 2. However, you have to remember, sine to the n is on the left side also of this equation, so it's on both sides. So I can treat it as a variable, and I can add it to both sides to cancel it. So how about we add n minus 1 times this integral to both sides? If we do that, then we'll end up with n times the integral. It's kind of like if I have x equals n minus 1 times x, then adding that to both sides, I get x plus, oh, it's supposed to be minus because this is minus. So I get x plus n minus 1 times x. So 1x plus 1x cancels, and you just have n times x. Maybe try to convince yourself of that. You can play around and plug in some numbers for n. You could see that definitely it's consistent with everything you've always done in algebra. It just looks funny because we have such big variables in the forms of these integrals. So let's see if I can manage to write this entire thing out without making a single typo. You'll be the judge. And we just have to divide by n. So we get sine to the nx dx equal to minus 1 over n cosine x sine to the n minus 1 plus n minus 1 over n times the integral of sine to the n minus 2 x dx, which is exactly the formula that we wanted to prove.